Machine learning in supply chains usually asks one primary question before dispatch: will this package be late? The industry operates on a straightforward assumption. If an algorithm can accurately flag future delays, managers can intervene, fix the routing, and optimize overall performance. But a purely risk-based view treats every flag delay as an equal operational priority. Pushing every at-risk order into a costly expedite queue ignores the actual economic value of the intervention. A warehouse might spend $50 in premium logistics to save a delivery that only generates $10 in profit. Classifying operational risk without knowing the financial context forces warehouse resources into a blind, inefficient allocation. Consider the hazard of rushing a high-risk order that already carries a negative profit margin due to heavy discounts or high baseline shipping costs. Applying premium interventions to that specific order actively compounds the financial loss entirely for the sake of preserving a superficial on-time delivery metric. The DataCo Smart Supply Chain dataset project provides a testbed to address this exact operational blind spot. To solve this single signal fallacy, the analytical architecture must combine two separate models: a classifier to predict delivery risk and a regressor to estimate order profitability. Fusing these models creates a unified risk margin matrix, shifting the objective from merely predicting delays to executing informed pre-dispatch triage. This architecture operates under a strict operational constraint. It can only ingest leakage-controlled data available before a package ever leaves the facility. Analytical Objective 1, or AO1, constructs the baseline classifier, designed exclusively to evaluate late delivery risk using those early signals. This ROC curve comparison chart tracks the performance of our risk models. The gray line represents a standard logistic regression baseline, while the blue line tracks an XGBoost classifier. The XGBoost model achieves an area under the curve of 0.775, proving stronger discrimination on the validation data. However, at the chosen operating threshold, the model has a recall rate of 0.584. It correctly identifies just under 60% of actual late deliveries. Despite missing a portion of delays, this classifier reliably isolates the most probable failures, establishing a working operational risk axis. Yet, while XGBoost effectively flags packages in danger, the algorithm has no way to tell a manager which flagged orders matter to the bottom line. That gap requires Analytical Objective 2, estimating the expected profit margin of an order before dispatch. This requires an architectural shift from binary classification to regression. The pipeline deploys a Gradient Boosting Regressor to predict continuous financial values. Looking at the validation scatter plot for this profitability model, we plot the actual profit per order on the x-axis against the regressor's predicted profit on the y-axis. Notice the tight horizontal clustering of predictions. While the model tracks the general direction of profitability, the root mean square error of 95.62 indicates notable variance between the estimate and the final realized profit. Because of this variance, the model is strictly for stratification, not exact financial forecasting. It separates the high-margin winners from the financial liabilities. This estimated margin output provides the supply chain manager with their missing value axis. Used as a triage tool, this regression layer identifies which targets are worth saving before any shipping resources are committed. The true utility of this pipeline happens in the third layer, the AO3 integration. We map the outputs of the two independent algorithms onto a single coordinate plane. Delivery risk sits on the x-axis, and expected margin occupies the y-axis. First, we draw a hard vertical decision boundary at the 35% risk mark. Next, we establish a horizontal boundary right at the zero margin threshold. The intersection of these two cutoffs instantly fractures the plane into four distinct operational quadrants. These zones translate into four specific directives: protect high value at risk, preserve service, expedite selectively, and standard process. When over 34,000 held-out validation orders are fed through the pipeline, they are dynamically plotted and distributed across these actionable zones. This matrix takes two streams of complex machine learning data and translates them into simple, scalable rules. The theoretical structure of the matrix is logical, but its business value requires empirical proof in the data. This chart illustrates the problem perfectly. Look at the middle bar representing the standard risk-only methodology. Under that single signal view, nearly 14,000 individual orders form a massive 99.6% monolith of high-risk deliveries, all demanding identical high-priority treatment. Now observe the result of applying the combined AO3 framework to that exact same population of orders. The monolith shatters entirely. While 39.9% of those orders correctly fall into Protect High Value category, a large subsegment splits off. AO3 isolates orders whose expected margin is too low to justify expensive logistical recovery, categorizing them for selective expediting only. By combining both signals, the framework identifies margin-saving operational subgroups that are completely invisible to a standard risk classifier. Instead of a binary choice between late and on time, packages route into 4 highly contextual lanes dictated by their combined risk and value scores. However, this architecture has a strict boundary. It acts as a non-causal triage layer, not a fully automated intervention system. The AO3 layer is designed specifically to guide human managers, helping them allocate their scarce warehouse resources where they will have the highest impact. Its primary function is defensive, preventing the blind automatic expediting of unprofitable orders. Isolating operational urgency from true economic value is what elevates a basic algorithm into mature decision intelligence. This framework has limitations. The threshold-based segmentation relies on fixed cutoffs that will require continuous recalibration across future scoring periods to remain accurate. Future iterations will need to test adaptive thresholding, adjusting dynamically based on shifting variables, like geographic region, target market, or specific shipping modes. Modern data science can no longer afford to predict single operational outcomes in a vacuum. It must contextualize complex business responses. The next evolution of supply chain machine learning relies on engineering composite frameworks that reflect the multidimensional reality of the business.